Assalamu alaikum. In this lecture, I will do two things. The first thing is the multipole expansion, and the second thing I will talk about the dielectric materials and derive an expression for the electric displacement. Let's talk about the multipole expansion. Assume I have a local distribution rho of x, then the potential at point P is given by this expression. Now let's write the denominator 1 over x minus x prime as this form. Here I push r outside, we get this form. The gamma is the angle between the two vectors. Now using the generating function of Legendre polynomial, we can write 1 over x minus x prime in terms of the Legendre polynomial, the first expression for r prime greater than r, the second expression for r prime lesser than r. In a compact form, we can write it as a single term. Now the angle between r prime is given by this expression. We also have from previous lectures the PL of cosine gamma is given in terms of the spherical harmonics. So substitute this in the 1 over x minus x prime, we get this expression. Now let's take our field point greater than r prime, that's r greater than r prime, and use the second expression for 1 over x minus x prime and substitute this in the phi, so we get this expression. Now let us rearrange this expression. The primed quantities given what's called the q sub Lm, the coefficients of multiple moments. So phi can be written in this form, where q sub Lm is the coefficients of multiple moments. In Cartesian coordinates, we have to expand 1 over x minus x prime as a Taylor expansion. So doing so, we get this expression. This is Taylor expansion. For n equals 0 gives you the first term for the monopole term. The second term gives the the dipole term. The third term gives the quadrupole term, and so on. So this is the simplification of the second term, which gives P dot R over R cubed. P is the dipole moment. We can write phi as monopole term, Q over R dipole term, and the quadrupole term. The Qij is defined in this expression. This is a second rank tensor. It's a traceless tensor. Now we have two expressions for phi. The first one in terms of the spherical harmonics, and the second term in terms of the Cartesian coordinates. If we look carefully at these two expressions, in spherical harmonics we have 2 plus 1 multiple moments. In Cartesian we have L plus 1 times L plus 2 over 2 for the multiple moments. The second thing that QLM depends on the choice of the origin. Now let's calculate Q sub Lm for some multipoles for Q00, 0, that's L equals 0, M equals 0, so this gives you Y00, Y00 is 1 over square root 4 pi, integration rho x prime d3 x prime gives us Q. Q11, similarly you have to substitute for Y11 star from the box, so we get this expression. And now for x prime we use r prime sine theta cosine phi prime. For pi prime we use r prime sine theta cosine prime, and for z prime we use r prime cosine theta prime. And simplifying this term, we get that Q11 is constant times px minus I py. Q10 gives constant times p sub z, the dipole moment along the z axis. For a negative m, we can use this expression for QLM, which is minus 1 to the power m QLM star. Now to get the electric field, we have to take the gradient of phi in spherical harmonics. This is the radial component, this is the theta component, this is the phi component. For the phi component, note that we can write dy lm by d phi as Im constant time y lm of theta phi. So this gives you a phi. As an application of the above relations, let us consider that we have a dipole located along the z-axis. That's P equal Bz. This is the P. So in this case, L equal 1, M equals 0 plus or minus 1. So X prime is Z prime because the dipole is located along the z-axis. And X prime Y prime is 0. So for substitute here Z prime, we get this Z prime rho of X prime d3 X prime. This is the definition of the dipole along the z-axis. Bx now is 0. Similarly, if you y1 minus 1 for negative m. So now let's take E sub r, substitute, we get this 2b cosine theta over r cubed, and there is theta components, which is b sine theta over r cubed. The phi component is 0. Now we can write it in terms of unit vector n in the direction of x minus x0 over x minus x0, which is this is the separation between the field point and the source point, and directed in this direction. So substitute here for, and we finally reach this. We already know this expression. Now let's move to multiple expansion of energy of a charge distribution in external field. We have a distribution rho subject to external field. Now W is the electrostatic energy is given by integration of rho phi of x d3 x phi. As we are assuming that we will assume that phi is a slowly varying function over rho, so we will expand it about the origin. A Taylor expansion for this is given by this expression about the origin. Now let's simplify the third term by subtracting this term, and then do a little algebra. We finally reach to this term. So and substitute in W for phi, we get this expression. This is the first term corresponding to the monopole term. This is the interaction with the dipole term. This is the interaction with the quadrupole term. In a nuclear physics, the quadrupole term is the most important. Now let's take two dipoles and calculate the interaction energy between them. This is an easy stuff. You just multiply this relation P dot E, and doing these calculations, one can reach easily to this result. Now let's talk about the electrostatics in the presence of media. Now going from microscopic to macroscopic, you can read the textbook, your textbook, or read it from Wooten. Now in any case, this relation holds, and for microscopic case, and this is for macroscopic case. Therefore, we can still get E from phi. This figure shows that when there is no electric field, the positive charge at the center, and the electric clouds is around the center. So when you apply a field, there is a shift in the center. We get what's called a polarization. Now, this is another schematic diagram how to get a polarization. We will define P as the polarization as the dipole moment per unit volume. So it's dP by dV. Now let's derive electric displacement or see what's the effect of polarization. Here we have a distribution rho of x prime. This is the field point, and there is a known polarization P of x prime. Within this element volume delta V, we have number of dipoles delta P equal the polarization, which is known to us, times delta V. Again, del P is known in this case. We assume there is no higher order terms. Now the potential at this field point is due to the charge distribution itself plus the contribution from the dipole moment. This is the monopole term, and this is the second term. Now substitute for delta Q by rho times delta V, and for the delta P, the dipole moment in terms of the polarization, which P times delta V, and then integrate over the volume V. Note that the gradient prime of 1 over x minus x prime is given by this, so substitute this in the previous expression and perform the last integration by parts or using this identity. Then we reach to this form, which is rho of x prime minus gradient prime dot p over x minus x prime. That means we have to replace our rho by this expression, two terms, the monopole and the dipole contribution. We have divergence E equal 4 by rho. Rho now is replaced by this expression. So we have divergence A equal 4 pi of rho minus gradient P. Take this to the left side. We have divergence of A plus 4 by P equal 4 by rho. The term between the two brackets, define it as D. It's the displacement, the electric displacement, which is 4 pi times the polarization plus A, the electric field. Now rho in this expression is the free charge. So divergence D equal 4 by rho free. This is Gauss's law for electric material. Now let's take linear materials. That's P, the polarization is directly proportional to E. The proportionality is chi sub E, called electric susceptibility of the medium. Chi in general is a tensor of rank 2. It has 9 components. Now we know that D equal E plus 4 pi times P. Substitute for P, we get D equal this expression times E. This thing between the two brackets, we call it epsilon, which is the dielectric constant. This is shows how P can be written in tensor form. Now if the dielectric is isotropic and uniform, then epsilon is independent of the position. So we have divergence E is 1, or you can push epsilon outside 1 over epsilon divergence E, which is 4 by rho over E. So in order to work with E, you have to use the reduced charge rho over epsilon. All problems in the previous chapters for the can be treated with reduced, if you have the electric material, by reduced charge rho over epsilon. Finally, let's remind you with the boundary conditions. As you cross D, you apply Gauss's law, and there is a jump in the normal component of the electric displacement. If there is no surface charge density, then the normal component is continuous. For the tangential component of the electric field, it's continuous. We apply here Gauss's law. We know this in the first class of this semester. Thank you.